All right, welcome back. So for this lesson, we are just going to be looking at how to calculate pH in something called pOH. So of course, this is just kind of a way around the concentration of hydronium or hydroxide inside of an acid and base solution. So for our pH, or higher hydronium ion concentration, pH is defined by the negative logarithmic to the base 10 of the hydronium ion concentration. So all that means is that if you want to get pH, you just take the negative log function of the hydronium or the hydrogen ion concentration. Because remember, they're both, actually, no, I have that over there. I've never seen that. So they just mean the exact same thing. So, of course, for this, you'll need to make sure that your calculators have a log function. So if you have one of the Texas TI-83 Plus ones, it has a log function on it. If you have a different scientific calculator, hopefully it does have a log function. Now, because we're using a log function, the significant digits for pH are going to be a little different than how we've done it in the past. So for significant digits, is the number of digits following the decimal point in the pH or pH unit is equal to the number of significant digits. So what that means is that we don't care about how many total significant digits are. It's only after the decimal point. So for example, if we have a pH of 12.335, we only look at, because this is a pH value, we only look at the number of spaces or digits after the decimal, and we got 1, 2, 3. So I got 3 significant digits. Now for pH of 0.12, same thing. This is a pOH. It's still on that log scale. So we only look at points after the decimal. So that's just 1, 2. So it's 2 significant digits. There's a few other ones right here. Now just be careful with this one and this one, because these are concentration of hydronium and hydroxide. They're not pH or pOH, so their significant digits are going to be how you've done it in the past. All right, so just pause the video and fill this in, because I'm going to put the answers up in 3 seconds. And this is for all the other ones. So this right here, 1.0, it's pH, so 1 point after decimal, so 1 significant digits. Hydronium ion concentration, we count it like normal, so there's 1, 2, 3, so hence 3 significant digits. pH 12.4, 1 point after decimal, so 1 significant digit. And concentration of hydroxide, same thing, we have 1, 2. It's not how many points after decimal, because this is a concentration, so we have 2 significant digits. All right, so just be careful with these here, and this is going to definitely play a huge role when we get into our calculations. Now, as I said before, is that if we are given, for example, like this, example 1, we're going to use the equation on the previous page. So given a hydronium ion concentration of 6.8 times 10 to the power 8 moles per liter, calculate the pH. So first thing, this is a concentration. So there's 2 significant digits in this one. So if we want to get the pH, it's just negative log concentration of hydronium. So that's negative log of 6.7 times 10 to the power negative 8. And when you put that into your calculator, we will get 7.17. Now I'm going 7.17 because this is 1, 2, 2 significant digits. Now, what we have right here, the method, so how to use log on your calculator. This is just kind of if you have the Texas TI-83 Plus, so you click the negative first, then log, then your brackets come out, so you go 6.7 exponent or times 10 to the power of negative 8, and then equals, and you should get your answer. But depending on your calculator, the keystrokes might be a little bit different, so just please play around with it until you get your answer for this one right here. Now, same thing, example 2, try this one on your own, see if you can get it, because the answer is going to go up in 3 seconds. And if you plug everything in correctly with 2 significant digits from our 4.7, we should get a pH of 10.33. Now, the reverse of this, if we want to find the concentration of hydronium and we're just given pH inside of a question, we're going to use this formula right here. So concentration of hydronium is 10 to the power of negative pH. So just remember the whole significant digit rule, because if we have an example like this, a solution has a pH of 5.35, remember this is two significant digits. Because it is a pH, calculate the hydronium ion concentration. So we plug in our formula, we go 10 to the negative 5.35, and we should get an answer of 4. Oops, sorry. Well, we get 4.6. I'll fill in a lot and then just round. This is unrounded, then of course rounded, we need two significant digits, so that is 4.5 times 10 to the negative 6 moles per liter as the final answer. So that is how we use that equation. So of course for our next one, you should pause the video and try this one on your own. But the same thing, so how to use calculator, second function log will get your exponent value, and then you can put in your negative 5.3. Forgot that other value there because it was 5.32, I believe. And then equals. So try this one on your own, see if you can get it, and the answer will go up in 3 seconds. And when you're done, you should get an answer of 4.7 times 10 to the power negative 11. Of course, we have two significant digits right here, so 4.7 times 10 to the negative 11 moles per liter, because we have 10.33. There's 2 spots after the decimal. So one of those things, again, just be very careful with the significant digits, and just be cautious if you're dealing with a concentration or a pH. Now, for our pOH, as you can imagine, if pH stood for power of hydrogen, then pOH is going to be power of hydroxide. So this is just using the exact same ideas about pH. We're just using it to describe the hydroxide ion concentration instead of the hydrogen. So the pOH of a solution is the negative log of base 10 of the hydroxide ion concentration. Also, pH and pOH are related to each other by this following equation. So no matter what, because hydroxide and hydronium are in every solution due to the ionization of water, but if you get the pH and you add the pH of the exact same solution together, we should get 14. So this will always hold true. So now we can actually go between if we have a hydronium ion or if we have a pH of a basic solution and we want to find pOH and everything like that. So you'll notice that the formulas are the exact same for pH and pOH. The only difference is right now, if we have pOH, we're going to need to use a hydronium ion. Just like when we had pH, we use the hydrogen ion concentration, right? pH and H. So this is just a way to make sure that you know that you're using the right formula, is that whatever's in your, after your P and your pH or your pOH, it should match up with what's in your log function there. So let's look at our first example. We have the hydroxide ion concentration in a cleaning solution is determined to 0.277 moles per liter. What is its pOH and pH? Now, first thing, just look at this. So this is the hydroxide ion concentration. So this is a concentration. So we have 3 significant digits. Now, first of all, because we have hydroxide ion, we can only solve for pOH first, because this is hydroxide, so it's only pOH. So we go negative log 0.277, and we should get an answer 0.55. And rounding the last one, because it's 7520230, we get 0.558 for 3 significant digits. So this is the pOH. Now to get the pH, we're going to use this equation right here. So when we rearrange, these are added together, so we do the operation of opposites. So in order to get pOH over this side to isolate for pH, we subtract. So So our of pH is equal to 14.00 minus our pOH. So pH is just 14.00 minus our 0.558, and we get a pH of, in this case right here, oh, sorry, just 1 second, gotta find my answer here, and we get 13.442. Now, this should kind of make sense, is that because we know we have a basic solution here, and the concentration of hydroxide is really high, so we have a really high pH, so it's very close to 14 here. And of course, because this is a pOH, we still have our 3 significant digits as well. So that is how we use our new function right here, and then of course, this right here, pH plus pOH is equal to 14. And of course, just because these are kind of mirror images of each other as well, if you're given the pOH and you want the concentration of hydroxide, you can use this formula right here, which is basically the exact same thing as our pH formula as well. So as long as you're given a pOH, and this is 2 significant digits, we can plug into our formula. And we should get an answer of 5.0 times 10 to the negative 7 moles per liter, and that, of course, that is 2 significant digits. Now, make sure, put these numbers into your calculator just to make sure that you're getting these values, just so you can fully use this log function, so the pH and the pOH and everything like that. Now, with all this here, of course, there's stuff in your workbooks to kind of help you along with all this, just to kind of make sure that you're getting everything. But now, because if you look at the pH and pOH where we're dealing with hydroxide and hydronium, those are ions. So we can actually use stuff that we did from last week, and that is concentration of ions, and we can put this together now with pH and pOH to kind of expand our knowledge. In this way, we can start off with either a full molecular compound like a weight or a volume of something, and we can estimate what the pH of a solution should be based on what we have. So for example, our first problem right here, and this is putting everything that we've learned together, we'll notice it says calculate the pOH of a solution that has 5.8 grams of lithium hydroxide dissolved in 250 milliliters of water. So just remember, in order to get pOH, we use that formula, so it's a negative log concentration of hydroxide. And remember, hydroxide is an ion. So this is where we use concentration of ions to solve questions like these. So our first step, of course, for concentration of ions, we need to write out the dissociation equation so we can get all the molar coefficients. So we have lithium hydroxide. Now I'm writing AQ because if you check the back of your workbook, you'll know it is aqueous. But the reason why it is a solid right here is because we're initially weighing at 5.8 grams. So lithium hydroxide, being an ionic compound, will start off as a solid, but when we put it in water, it's going to dissociate into the lithium ion and the hydroxide ion. So remember, this is that. So this is why we need to do this concentration of ion step and figure out what is the concentration of this particular ion. Now, given our information, there's a few steps that we need to do. First of all, this is just dealing with that mass, right? Because remember, in concentration of ions, after you write out your dissociation equation, your first step is always trying to find the number of moles of whatever that's there. So in this case, we go number of moles. Oh, I'm just going to change the color back to the blue. So we're going to get the number of moles of lithium hydroxide first. So it's the mass of lithium hydroxide over the molar mass of lithium hydroxide. So the mass was given 5.8 grams. Now the molar mass of lithium hydroxide, we have 1 lithium, 1 oxygen, 1 hydrogen. When we add those molar masses together, we get 23.95 grams per mole. And then we plug this into our calculators and we get 2.42779 moles of lithium hydroxide. You don't need to write that here. I'm just trying to keep all my information there. Now next, because we're going to have to do the concentration of ions, and because that concentration of ions, we need to get concentration next, right? So that's when we go concentration of lithium hydroxide is number of moles of lithium hydroxide divided by the volume. So we have our 0.242779 moles divided by the volume, 250 milliliters. So remember, concentration is always in moles per liter. So this 250 milliliters is the same thing as saying 0.250 liters. And we end up getting a concentration of 0.97112 moles per liter of LiOH. Okay, so we're keeping it there. Now, we are not done yet, so that is the concentration of lithium hydroxide. Remember, we're all working towards getting the concentration of hydroxide, one of the ions. So now that we have the concentration of lithium hydroxide, I'm just going to have to scroll down, we get concentration of hydroxide. This is where we do our concentration of ion step, is equal to our 0.97112 moles per liter of LiOH, and we're going to have to multiply this by our conversion factor. Now, we want to get rid of LiOH, lithium hydroxide, so that shows up in the denominator. We want our hydroxide ion, that's in the numerator. And the numbers we use comes from our balanced chemical equation. Now, these are all blank up here because it is a coefficient of 1 in front of each. So, by doing this, lithium hydroxide cancels out, and we are left with 0.97112 moles per liter of our hydroxide ion. So one more step. I know this seems like a lot, but we've done these here where it was these three, actually 4 steps before, where we write out the balanced chemical equation, find the number of moles, find concentration, then the concentration of the ion. So really all we're doing is just adding our last step, pOH is equal negative log to the concentration of hydroxide. So we go negative log of 0.97112 moles per liter, and we are left with 0.01. The reason I'm keeping it at 0.01 and not all the other ones because we have 2 significant digits up here from our 5.8 grams and 3 significant digits from 250 milliliters, but we keep 2 significant digits right here. And that is it. Now, of course, not all the ones you're going to get is going to be this long. This is just one of the ones that kind of showing you where we can go with this, where we take kind of everything that we've done before. So technically this step here, this one, and this one you've done with the concentration of ion steps. We're just adding pH or pOH calculation at the end. Now, not all of them are going to be this long, but you might get ones like this. All right. So that's just kind of showing you why concentration of ions was so important, and I mentioned that during the concentration of ions video last week. So there are more examples to get done. So we have 2, 3, and 4, where I'm going to ask you guys to kind of work on those, and that'll be it. Now for the answers to these here, I want you guys to make sure to open up the answer key on I have posted up on Google Classroom for you. So if you think you can tackle these here, please just, you can stop the video and go on. I'm just going to go over the calcium hydroxide example just in case you need a little bit of extra help. All right. If not, check your answers for 3 and 4 in your PDF of the answer key. All right, so for those of you who want to see another example, just like the other one where it's a little longer, we're going to go over this one right here. So we have 10.3 grams of calcium hydroxide dissolved in 500 milliliters of water. What is going to be the pH and pOH? So we're going to get both. All right. Just like before, we're going to start off with writing out the dissociation equation because we have calcium hydroxide. So we got CaOH2. It's aqueous. It's going to dissociate into the calcium ion and the hydroxide ion. And of course, to balance it, we need to do this. Now, just like in the other example as well, we know we need to work towards concentration because where we need the concentration of the hydroxide ion specifically in order to solve for pOH. So we're going to have to go through our concentration of ion steps, and that is, first of all, get the number of moles of calcium hydroxide. That is going to be the mass divided by the molar mass. So the mass was 10.3 grams. Now the molar mass for calcium hydroxide is 1 calcium plus 2 oxygens and 2 hydrogens. So the molar mass for that is 74.10 grams per mole. And of course, when we do this in our calculators, we get the number of moles of 0.139001 moles of calcium hydroxide. So now with the number of moles, right, we need concentration. So that's our next step. Concentration is equal to number of moles divided by our volume. So we have the number of moles, which we just solved for, so 1.39001 moles divided by our volume. Now up here is 500 milliliters. Remember that we don't use milliliters in these equations, we use liters, so we divide by 1,000 to get 0.500 liters. And when we do this, we get 0.278003 moles per liter of calcium hydroxide. So this is fine. Now that we have a concentration of one of the things in our balanced chemical equation, we can use our concentration of ion step to figure out the concentration of the ions. In this case right here, the concentration of the hydroxide ion is what we need. So in order to do this, we get our 0.278003 moles per liter of calcium hydroxide. And we do our conversion factor. So remember, the thing that we want to get rid of is on the bottom of our conversion factor. The thing that we want is on the top. And the numbers that go in front for the conversion factor come from our balanced chemical equation. So the number in front of hydroxide is 2. The number in front of calcium hydroxide is 1. So when we do this, the units of calcium hydroxide will cancel out. And then we are just left with hydroxide, which the answer is 0.54006 moles per liter of hydroxide this time. And finally, now that we have the concentration of our ion, we can get pOH is just our negative log concentration of hydroxide, and we go negative log of our 0.54006. And from here we, go back, I found a mistake in this step right here. It's not 0.5400, so I'm just going to erase that. This isn't the number, it's just slightly off the calculations there. Sorry, just go back, I apologize for that. It's actually we should get 0.556. 0.556005. And same thing, we just fix that right here. that's what we get. And then of course when we plug this into our calculation or calculator, we get a pOH of 0.25 and 3 significant digits because of 10.3 and 5.00. We should get 0.2549, and of course that rounds to 0.255. And last but not least, we have our pH. Now we solved this on the previous slide, and that is pH is equal to 14.00 minus pOH. So that is equal to 14.00 minus our 0.255, and we get a pH of 13.745. And those are our two answers. So, of course, for these right here, in order to be successful, you still need to be very confident with the concentration of ion steps. So if you're still not fully confident with that, please go back and review concentration of ions before you tackle these questions here. Because if you're still struggling with concentration of ions when you get to these here, you are going to find it very difficult because you need to do concentration of ions in order to get to the pH and pOH ones. All right, so of course, if you are having trouble with that, please make sure to email me. We can set up a Google Meet where we can go over some one-on-one stuff and try to make sure that you understand these processes. So, of course, like I said, for the next 3 and 4, please just look online for the answer keys for that. And of course, if you have any trouble, just let me know. We can go over them. But that is it for this lesson. So our next one, we're going to be looking at something called indicators. And then that'll be it for this week. So I'll see you guys for the next lesson.